let's talk about multiple regression. All right, let's also pair my mouse with this computer so I can use it as a remote for the presentation. Oh, I did that already. Okay. So, a lot of times we're interested in simple one-to-one variable relationships. Yeah, of course. Last time, our last example, what was our example last time? It was IQ and income. That's a one-to-one relationship. That's interesting. I mean, it really is an interesting thing. A lot of times you'll look at things like IQ, which are, again, really interesting variables, and finding out if they are affected by some variable or another, and just one variable. And that's fine if it's just one variable. But sometimes we want to look at more than one variable. And this is going to be one of those times. I'm going to obviously explain to you how you do this. So let's pretend, and you might get this with IQ and income actually, you would get an R, let's say you get an R of 0.5. Okay? So R of 0.5. I don't know if you might need a little microphone. Sorry for doing that to whoever's ears that's in. So that's nice. I mean, I'd be ecstatic. Those of you guys who are into like sort of social psychology, personality stuff, rather than interesting psychology, realize I think that would be crazy high for a correlation in a personality or a social kind of context. So then you'd be ecstatic. But you know what? R is the covariance of xy divided by the standard deviation of x and y, as we know. So the question I'm asking here is how much variance is accounted for by one variable and the other? That means how much variance do they share? The hardest part of this material is thinking of variance as a thing you can kind of hold and touch. Variance is something you can kick. It's a weird thing to imagine. Once you can do that, this stuff actually is pretty easy. But that's a non-trivial task, thinking of variance as a physical quantity. But how much variance do these two variables share, or how much is accounted for by one and the other? Well, this is how you'd figure that out. Well, R deals with standard deviations, so if we're dealing with variances, let's square it. I mean, that's really all the logic of this. So if R, so we take R, so R squared would equal 0.25, because 0.5 times 0.5 is 0.25, right? Right. So what this is saying then, so our R squared, little r squared, and there's a reason I'm making that distinction, there's going to be a big R squared later, little r squared equals 0.25. So we've accounted for 25% or a quarter of the variance in IQ by looking at the variance in people's income. Or the other way around, we don't know what comes first. These things, correlation and regression don't deal with that. Design deals with that. Okay, so questions so far. So we've got a correlation of 0.5, and which means we've accounted for 25% of the variance in one by the other. Means there's 75% of variance left to explain. Why does other variance in, let's say we're trying to predict income. Where does the other variance in income come from? Well, there's all kinds of possibilities. But there's 3/4 of what's left. I mean, I'd be pretty happy with explaining a quarter of the variance in anything. That'd be wonderful in a variable like that, okay? And the kind of stuff that I do, that would be unacceptable. Okay, so because a lot of the things I do are more like psychophysics. So we did a thing with timing behavior in black-capped chickadees ages ago, and we explained 99.7% of the variance. Now, the thing is, that's what you're supposed to do with that kind of procedure. This is different. You're usually dealing with questionnaires. You're not dealing with chickadees pecking at touch screens. So it's a different kind of question. So accounting for 25 would be great, but there is 75% left, so let's find out what it is. So there must be other variables that account for the rest of the variance. Ergo is a Latin word, it means therefore. It's also an English word, but it comes from the Latin, which is unchanged. So we deal with this by actually bringing them into the model. So we're just gonna, if we've got another variable, let's find it and account for it, or have it account for the other variance. So we're just going to bring it into the party. We're not going to ignore it. We're not going to try to standardize it or something like that. We're not doing statistical to it. We're just going to measure it and then we have that other variable. All right, so I'm going to show you some pictures. What really helps, I think, here actually are diagrams, and I've got a couple here I can show you. So let's start with this one here. Okay, that's all the variance in y. So again, you have to think of variance as a thing, and it's not an easy thing to do because variance doesn't, it's hard to think of as a thing. You have to just imagine it's a thing, okay? So that's the variance in y, the predicted thing. We're predicting income. Right? So there's x1. Now see, they share a quarter of their variance. That's the variance in x1. So I'm calling x1, in this case, is going to be IQ, yeah? So it's IQ predicting income. So you can see that the variance overlaps, and I don't know if that's exactly a quarter. I tried to make it close. But it's supposed to be about a quarter. As an aside, I keep saying that, if you've got a 0.25 or a 0.5 correlation in any sort of questionnaire-based stuff, you'd be ecstatic, and you would be, because typically what they get is around 0.3. 0.3 explains literally 9% of the variance. There's 91% left, right? So you never explain this much. It doesn't happen very often, except with IQ. Look at IQ. But there's got to be other variables. So let's say what's another variable that correlates with income that we can measure? Think of one.
Background.
Which one?
Background.
How are we measuring that?
Like parents' income.
Parents' income. I like that. That's good. Yeah, and then, you know what? I bet parents' income accounts for a lot of it because of the socioeconomic status. Okay, that's what we were getting at, right? Yeah, there it is. So x2, we're going to say is socioeconomic status of your parents, your background. Exactly. That accounts for some more variance in y. Right? There's a whole other slice of variance it's accounting for. Right over here. Okay. All right. So that's a good one. Yeah, parents' income, background, very nice. So that's something we can measure, and then we can do a correlation, and then we can take out that variance. So we still have some more variance left here, but we've now explained 50% of the variance, assuming that was roughly the same amount. So that's what we end up doing. So conceptually, that's what we do. The math's a little more complicated than that, but not a lot more. It's not that bad. So in general, we have a model that looks like this. So remember before we had a model with just univariate regression with one variable regression, which was y equals a plus bx plus e, right? So here we have, y hat rather, y hat equals b sub 0. We're just changing the names to more general. B sub 0 is the same as the a in simple regression. It's the intercept. And then we have b sub 0 times, b sub 1 times x1, b sub 2 times x2, plus dot, dot, dot. B sub p minus 1 times x sub p minus 1 times plus e. This is saying then that we have p minus 1 predictor variables. So in our case, when we had x1 and x2, p minus 1 equals 2. You have p minus 1 predictors, meaning in your model you have p parameters because you have this, b sub 0, which you don't multiply times the next value. It's the one at the intercept, okay? So what this is giving us is just a great big equation. We end up with an equation at the end that says, your income equals this. Plus this times your IQ, plus this times your parents' socioeconomic status, like their income. Plus error, the stuff we don't know. So we have p minus 1 predictor variables, and again, the way to remember that is we have p in total predictors, but one of them isn't a variable. One of them is just the intercept. Okay. So this is for the data set itself. These are statistics, they're not parameters. So in the real world, there actually is, out there, somewhere, an actual, variables are related in the population, but this isn't about populations, this is about a statistic. So statistically, we're going to use Latin letters, so B's and X's. Okay, and we're going to use small letters. Small Latin letters are what we're going to use. what this is doing is trying to predict, again, predicted y, remember y hat, is trying to predict a combination of values that gives you the score for the variable, right? So in the population, it looks like this. Now it's just y. What this is saying is, not y hat, this isn't a prediction. This is saying y is a combination of these things. So it's beta sub 0, it's a Greek letter, plus beta sub 1x sub 1 plus beta sub 2x sub 2 plus dot dot dot, beta sub p minus 1x sub p minus 1 plus epsilon. Okay? Error is normally distributed with a mean of 0 and a variance of sigma squared sub epsilon, which it always is. In this case, and you're used to with analysis of variance, with that being with it being error variance, and it's not. This is just leftover stuff we haven't explained. So I guess it's kind of like error. So, but it's not a prediction error in a model in the population. It's just saying that's the leftovers. Okay, that's what we call it, residual instead of error a lot of times. We're gonna call it residual, but error is fine. It means the same thing. So again, what this is saying is that in the population, there really is a case where this variable y equals this plus this plus this, this plus this times this, plus this times this, plus this times this, plus something at the end. Okay? Questions on that so far? Okay. This is something that, again, I said the other day that it's very powerful, but it's also very tempting to look at that and go, well, then that means one thing causes another. Remember, it doesn't mean that. Yes, Jake?
So when you're going over to point like for the x2 plus and the dot dot dot, is that because you're doing it as many times for the groups and then you go into the p?
Oh, for as many times as variables you have. So
Okay.
you could have 25 variables.
Oh boy.
So you would have b sub 22, x sub 22.
Oh, okay.
Okay. So you typically wouldn't do that. It's what use is it for me to tell you that one variable is a combination of 22 others? That's not an interesting thing. If I can tell you, however, that it's a combination of 3 of them or 4 of them, that's actually pretty useful. And the example, and I used the example the other day of a friend of mine, I shouldn't say friend again because he's an acquaintance, but one did a thing. You ever find out who this is that I had anything to do with his misconduct? Wasn't at this university. I had nothing to do with that university. It's somebody I know from graduate school. Anyway, he collected a bunch of data on smoking. I was telling him about this the other day, and he was trying to figure out a way to get an accurate measure of how much people smoke per day. And there's an easy way to do that. I'll take a blood test. There's a problem with that. I gotta take a blood test. I can take a saliva sample. Again, I still have to take a saliva sample. And I gotta take it to a lab. You know what would be nicer? What if I could say, how old were you when you started smoking? And how many years have you been smoking? And have you tried to quit today? And have you quit before? And if you answer all those questions, I can make it and I have the numbers, like it's some number times the year that you started smoking, some number times have you quit today, 0 or 1, yes or no, or try to quit, that kind of thing. And you put those together, and I can get just as accurate an estimate of how many cigarettes you smoke as I could have with a saliva sample. So that's really brilliantly useful. And so now a physician can actually ask you 4 questions, and he or she doesn't have to send for blood work. It's amazing stuff, right? So that's the kind of thing you're doing here. You're trying to come up with, and by the way, he had 22 variables, well 23. There was cigarettes per day, and 22 other variables in the model when he was in the data set. And he narrowed it down to those 4 being the important ones. And the point of what all this course is, not this course, but this couple of lectures on regression is about, is how do you figure out which variables to use and which ones to go, nah, I'm not going to use that. Okay. So that's sort of what's going on here. That's like literally exactly what's going on here. So again, this is why, and this is saying, again, this is parameters. This is saying the world actually works like this. We don't know this, we never can know it. And if we knew it, we wouldn't have to do the study, because we already know. All right. So what we get, if we have p minus 1 predictors, we get a line. We just get a line, a straight line, like the regression line, like we had the other day when we talked about simple regression. Just a straight line with prediction errors. Okay? Think about it when you were in high school, you know. Y equals 3 plus 7x. It's something like that. Okay? It's really straightforward. First order equations, there's no squaring anything, nothing like that. Really straight ahead stuff. Stuff that you literally did in like grade 7. You were given lines and told with a piece of graph paper. I hope they still do this. Draw a line, here's the equation. Right? They still do that. I see Justin nodding. Yes, they still do it. Very good. I'm glad. I'm so glad they still do that. That's good. So you've done that. You've all done it successfully because you're here, right? You've done this. So that's all this is. And then you can look at the line and go, oh, the prediction, oh, there's the prediction. Now, if p minus 1 equals 2, we get a plane or a surface. How many people here in high school did 3-dimensional coordinates? Anybody do 3-dimensional coordinates? Okay, we don't teach that anymore, right? Okay, so 3-dimensional coordinates work like this, probably as you could guess. So if we've got 2 dimensions, just y and x, there's your line, but oh, we got z too coming out. So now it moves it like that. Now we have a plane or a surface. Okay, that's good. And again, you can just find out what your x and z values are up to the surface. Oh, okay, there's the y. So it's something, again, I think we can visualize. You can even draw, through some visual tricks, you could draw a 3-dimensional graph. I mean, I can't, but software can. So that's fine. And I think visualizing these things can be useful. Like I said, when you think about it like, oh, we used to draw lines like that in high school and even elementary school. That's stuff you'd be used to. Now the problem is if p minus 1 is greater than 2, we get something that is in more dimensions than we live in. Well, not technically. It's in 4 dimensions and we live in 4 dimensions. So you'd have to actually have you'd have to have the plane moving. So passage of time is another variable. I can't do that in my head. My brain doesn't work like that. I can't think like that. So I stop visualizing when I get to hyperplanes and hyperspace. Also, frankly, hyperspace sounds very kind of, Star Trek-y, Babylon 5, that kind of world. So I kind of like that. I'm kind of excited about that. The best to try to not visualize hyperplanes. I know one person in my career who could do this, and I've told you about Ian, my stats prof in grad school, and he said, it's pretty easy, but all you do is you imagine the 4th variable, it's moving, and then just imagine the colors changing. So you can do that. He goes, yeah, of course. No one else can, Ian. You're weird. But he could, and I believe him too. There's no reason to think he couldn't. He probably could. So, okay, there's a plane. So there's your hyperplane. Yeah, don't. See, because the color matters too. You don't want to. I told you don't visualize it. Your best bet is just not to try to visualize a hyperplane. It's not useful. If you can visualize a plane, that's great. And you can see, like, yeah, okay, that's a 3D graph. I get it. This is a 4D graph because it's got color. And a 5D graph has color and then the plane moves. Have fun with that. That stops being useful. It's not useful data visualization anymore. Right? I could put this in a paper and people would, I think, understand it. If I put this in a paper, I don't think anybody would understand it, except for my old stats model. All right. Okay, yeah, we're not actually done with ANOVA. The way you find out if your model is significant is you use analysis of variance. So to find out if our regression model, because the thing we come up with, that equation, we call that a regression model, and we want to see if it's significant, and we were going to see it's significant. Have we accounted for enough variance? That should sound vaguely familiar. That's what we've been doing for the last, 8-9 weeks. So we have 2 sources of variation here. We have regression due to the model, variance due to regression, so that's due to the model itself. And then we have residual error, if you want to call it that, but usually we use the word residual. Okay. My watch keeps thinking I'm talking to it, because if I look at it and I have to look close, And then my Siri thing goes off and it's like, well, regression is, I know what it is, man. Stop telling me things. So we're gonna see if our model is explaining a significant amount of variance, right? Because maybe that isn't significant, maybe that's just through sampling error, right? So that's what we do. So we get, yeah, it's ANOVA again. And it looks like this. We get a regression as a source of variation residual. So there's p minus 1 degrees of freedom for regression, n minus p for residual. And to get the mean square, you divide the sum of squared by the degrees of freedom to do the f. Mean squared regression divided by mean squared residual. And this analysis, by the way, is the whole model. So if we're thinking back to my acquaintances, cigarettes thing, of course those 4 variables would explain a significant amount of variance. Right? All together. This isn't about individual variables. This isn't saying time to first cigarette in the morning or the number of years smoked are important. This is saying the whole thing together is explaining a significant amount of variance, and in that case, in the variable cigarettes per day. And remember, the model is a thing that's a sum of its parts. Like, it's a linear combination. It's called linear regression for a reason. It's a linear combination, which means they're added up together. Okay? This times this plus this times this plus this times this plus this times this, etc. I mean, your regression model bloody well better be significant. It have to be. Right? If you got 4 or 5 variables put together, of course it explains a significant amount of variance. So we want to know how much of each variable it's explaining. We're much more concerned with how much extra variation is accounted for by adding a new variable in the model. So think about going back to our original example, which is we're going to predict people's income by their IQ and their parents' background, their parental income, their socioeconomic status. Great. So once we've explained the variance due to IQ in income, when we bring in the other variance, which is variance due to parents' income, parents' socioeconomic status, that should explain some extra unique variance in income. Now, would you think there would be overlap? Like, it would also explain some of the same variance? In other words, just think about it. Do you think people's parental income also is related to their IQ? I think it is, because if your folks have more income, they can buy you more books. You eat better. They know that like crazy, right? So all that's possible. So maybe it's going to be a bit of overlap. We want to see how much of it is unique. We're looking for unique variance. So extra stuff. We're trying to explain extra stuff. So the way one of the things we can look at is how much big R squared goes up. Big R squared is measured using sum of squared regression over sum of squares total. So it's giving you a percentage of variance your model explains, the whole model together. Big R squared. Okay. So we add a variable in. So if you have a model, let's say 5 variables, and you add a 6th variable, does R squared go up? Well, it has to, because you're explaining extra variance every time you bring in a new variable. It could stay exactly the same. That's possible, but that would mean that that variable already in there. So if we said IQ measured on one IQ test and then IQ measured on another IQ test, they'd overlap a lot. There wouldn't be a lot of unique variance. But there'd be something. So it kind of has to go up. The question is by how much? And this is the weird part. You kind of determine by how much. It's up to you to say, is this enough that I think this matters? So is it enough to deal with the loss of degrees of freedom and the extra complexity of the model? So whenever we bring in a new variable, we lose some explanatory power, right? Wouldn't it be great if we could just have one variable and say this equals that, or 2 or something? But every time you bring one in, it makes it a little more complicated and you lose some degrees of freedom. And think about the complication of going from a line to a plane. Okay, a line to a plane isn't bad. If you're used to, you play with graphic software a little bit, you get used to planes pretty quickly. A plane to a hyperplane becomes incredibly difficult to visualize. So, and you know, there's something to be said for not being complicated. Just saying. There's extra complexity, and extra complexity isn't always a good thing. So we have to look at something other than our square, because it's always going to go up. We have to find some quantity that could go up or down. And there it is. Don't worry, you're never going to have to reproduce this. I'm telling you what this thing is. And this is called adjusted R squared. That's why it's got an A at the bottom. So it's you can actually just see here it's weighted n minus 1 divided by n minus p. It's allowing us to, because it's weighted like that, we end up getting, it can go up and down, it can fluctuate. It can fluctuate. So if you add enough new variables, it can go down. If it goes down, you don't use it. Just don't use that variable. Okay. So here's the kind of here's a question that you might get asked on the final exam. It'll be a little more involved in this, but not that much more. Which one of these is the best model? This is a model with just x minus 1, x1 in the model. There's just one predicted variable, and it's x1. And here are the values for the sum of squares for regression and residual. Put that one over there. There's the x2. That's just with x2. So x1 is not in this model. This one just has x2. So you can see it's explaining a little less. You look at the sums of squares, it's explaining a little less. Oh, we could do x1, x2. x1, x2. Explains a lot. Now, I know I've not even told you how to pick them, but I bet you can probably do this a little bit intuitively. Which of those do you think is the best model? Which one does the best job predicting? Which one, remember, we're predicting something called y. We don't know, it doesn't matter what it is. Which one do you think does the best job there?
Thank you.
I think we can all see which one does the worst job. Right? This one here. So that's 30 out of 130, because that's sum of squares total. What's 3/13? It's about 30 something. So this is x2 something. x1 on its own is nice, 50 out of 130, that's pretty good. 5/13. That's a little under half, right? Yeah. Now the model x1, x2, ooh, 8/13, 80 out of 130. But this one, remember, this one, because it's got two variables, this is now a plane. This isn't just a straight line, this is a plane. It's a little more complicated. So I think the loser is the one in the middle here, x2, and it's between x1, x2, and x1. Between x1, x2, and x1. I would probably do the one with 2. It's explaining more variance, a lot more. And you know what else? x1 and x2 don't overlap. I can tell that by looking at those numbers. So what I'm saying by that, and I'll show you how I can figure that out in a second, or maybe somebody can figure it out. So if we have y, so those are the variance in y. Here's the variance in let's make that x2. Yeah. Here's the variance in x1. Notice how I don't have x1 and x2 overlapping, right? Because think about that. If we had a case where we were explaining, so let's bring in another variable, we'll call it, we'll change colors on the board here, we'll use green. Let's say I had x3 here. The only unique part it's explaining is here. We wouldn't want to use x3. It's explaining hardly anything extra, but what it's doing is making things more complicated. And it's also, look at this, look at how much it overlaps. These couple of places, all this variance has already been explained. But I said here that x1 and x2 in this case do not overlap. Can anybody figure out why I said they don't overlap? Look at the numbers. So what I'm saying is that x1 and x2 are both explaining unique variance in y, completely on their own. What do you think? What can tell you how much variance is explained? What do you think? What do you think can explain? The degrees of freedom load. So it's obviously something to do with the sums of squares. Okay? Look at the sum of squares column in those three tables. It's a neat thing here. Always adds up. First of all, notice how it always adds up to 130. It has to, because it's the variance in y. The total is the variance in y, and there's 130 units of variance in y in this case, okay? Now look at x1, it's 50, and x2 is 30, and x1, x2 is 80. 50 and 30 is 80. If they overlapped, it would be less. It would be like 70 or 60 or 63 or 71 or 58. It could not be greater than 80, but it would be less than 80. So we would say here that this is the other reason we would definitely choose this model here as the best one, because these two variables, x1 and x2, are completely independent of each other. They do not overlap. That doesn't happen. In the real world, this doesn't ever happen. Things are related to each other. Our universe is like that. It's incredibly rare when two variables don't relate to each other. Usually they're related so small that it doesn't matter. Well, I shouldn't say usually, a lot of times. But here we have no relationship at all, so I would jump at that. I'd be jumping at that. Okay, so how do we end up getting these sums of squares? Well, I talked the other day about type 1 and type 2 sums of squares, and this is where this is going to be important again. Type 1 sums of squares depend upon the order you put them in the model. And type 3s don't. Remember that? Or sorry, type 2s don't. So let's say we have a 3-variable model. So we have y, and then we have 3 possible predictors, x1, x2, and x3. So, you know, IQ, parents, socioeconomic status, and number of years you've been in school. That's 3 variables that are going to predict income. So we get different kinds of sums of squares. So we have a type 1 sum of squares. It's just how much variance, this is basically the sum of squares regression, for x1. Now, once we bring x2 in, that's x1 and x2 together. When we bring in x3, it's x1, x2, x3 together when you're using type 1 sums of squares. Notice what type 2s are. They're x1 with these two in the model, x2 with these two in the model, x3 with these two in the model. So that line there just means given. So x1 given x2, x3, x2 given x1, x2, etc. So you can see that the type 2s are really useful because they give us unique variance. They tell us what extra are these variables bringing to the party. Are they bringing anything extra, or are they just wasting our time? Oh, look at that. All right. So you might be asking yourself, self, why should I care? Well, because I told you to. That should be a good enough reason, young lady. But I think I called my daughter a young lady once. It just seemed so like something you don't say. It's weird when you are a parent because suddenly you start talking like your parents. And some of the things you say, you go, oh, I see why they said that. Other times you go, I can't believe I just did that. Right, Jake? This happens, right? Okay, so I'm just the other parent in the room is corroborating what I'm saying. And by the way, that goes until they're in their 30s. Just letting you know that it keeps going. So if there's a correlation between, no correlation between the variables, type 1s equal type 2s. If there is a correlation, type 1s don't equal type 2s. So the only reason I'm telling you this is because if you are out there choosing variables, one of the diagnostic things you do, notice how this is, well, you could do this, you could do that, a lot more judgment on the user's part. This isn't, oh, the computer says it's this. There's a lot less of that. There's a lot more of, what do you think and why? That's why this is left to the end. So you will be looking at type 1 and type 2 sums and squares and going, well, they don't seem equal. That means there's a lot of overlap. Like, these are diagnostic things. That's what these things are. So, and again, I'll talk a little bit more about that as we go on. So the thing that's important for our purposes is, when we talk about type 2 sums and squares, is what do they give you? And type 2s give you the extra variation accounted for by having a variable in the model, given that the other ones are already there. So this is put into words what a bunch of math that I'm not going to show you does. Okay? Because the math, who cares? It's not important for our purposes. You can learn all about it in graduate school. It's not for what we're going to use this for. You'll be fine. By the way, remember thesis conference Friday, Quattro, 12:30 is when it starts. And I think it ends sometime next century. It's going to be a long one. Well, it's about 5 o'clock. Anyway, if you want to come and hear some of your friends give their talks, you should come. Just say. All right. You're going to see a lot of people talk a lot about statistics, and you're going to understand it all. So what's this going to give us? What can type 2s give you? Type 2s can give you a coefficient of partial determination. Ooh, that sounds nice and important. It's kind of the opposite of big R squared. Remember, big R squared is how much do all the variables together explain. What the coefficient of partial determination does, I was having trouble talking there. I was afraid I was going to start smelling burnt toast there for a second. Anyway, so this is going to give us how much unique variance each variable explains. Very useful quantity. So in fact, would you look at type 2s? No, you get the computer to do that, and it gives you our big adjusted R squareds. Yay! It's going to give you some R squareds. It's going to give you, or partial correlations, partial determination. So, okay, this is all the variance in Y. Now there's X1. So I'm just trying, there's 2 ways I've figured in my career to visualize this, and one of them is a Venn diagram. The other one are things like this. So if all the variance in Y is in this bar, then the variance in X1 that overlaps with Y is right there, okay? Everybody understand that? There's X2. So now we have extra stuff we're explaining. So you see that's good because look, it's unique variation. They don't overlap, these two. It's unique variation that hardly ever happens. So when it does happen, you grab that other variable. I mean, it's useful. Now, here's another situation. So that's Y, and there's X1. Now, if X2, that's this here, is explaining not unique variance, but some overlapping variance, some of the same variance X1 explains, this should fill up that bar a little less. So that's what I'm saying here is now, in this case, even though it's the same amount, and this was the same amount at first, remember? But this x2 also overlaps with x1. Now, think about the ultimately stupid example of this, because I think because sometimes ridiculous examples are really instructive. What if y again was income, and x1 was your score on the Wechsler Adult Intelligence Scale, and x2 was your score on the Raven Progressive Matrices IQ test, which is just another IQ test. You would expect even worse. You might expect, in fact, it to almost just sit on top of it. You wouldn't use 2 IQ measures. Why would you? Well, what this is saying is, look, on the one on the right, x2 is mostly just x1 and a little bit extra. Why you pick one? And I'd pick the bigger one, so I'd take x1, I wouldn't use x2 at all. I'd throw it away. It's not explaining enough extra. Look at how much extra it's explaining. Look, this little sliver here. It's not worth it. It's not worth it. I'm making my regression model more complicated. I'm losing degrees of freedom for what? For nothing. Well, it went backwards. That was weird. But it didn't go back. Whoops. Well, I broke that. That's good. I will sit here and talk about this while I try to repair this admittedly 30-year-old mess or 20-year-old mess. So you can square that and get a thing called the coefficient of partial determination. I think it's going to be fine, unless that's a part of it. Yeah. Let's see. This may be more complicated than I want it to be. I think I have it. Yeah. I'm pretty much at this point an engineer. When you think about it. Still work? Oh yeah, it does. Okay, let's go back. Okay, good. Yeah, right. So why does this matter? Right. So sorry, I'm going to go back just one bit here. Okay. No, damn it, dummy. Losing my mind. Okay. Yes, extra, that's where it was. So the coefficient of partial determination, which is the thing that makes you drop your mouse, is the extra variation accounted for by another variable in the model. You can square that. Sorry, take the square root of that, I should say, and you get the partial correlation. So it's basically a statistical way to control for a variable. Okay, you might see coefficient of partial determination or partial correlation in papers you might read now and then. Okay, so again, now back to this. Why does this matter? Let's think about the model. The model says y hat equals b sub 0 plus b sub 1x sub 1 plus b sub 2x sub 2 plus dot dot plus b sub p minus 1x sub p minus 1 plus e. Right, that's what the model says. Nothing there about, is there anything there about putting two variables together? About variables that overlap? Is there anything there with multiplying x1 and x2? Nope. Nope, there's nothing there saying that. It's just saying this times this plus this times this plus this times this plus this times this plus this equals that. There's nothing in there about and x1 and x2 go together sometimes. It doesn't say that. If the model doesn't say it, you have now violated an assumption. So every time you get this overlap in your predictors, which is almost always, you're violating an assumption of the model. This thing may be on its last legs. Just picked it up and this part just came off. So this actually has a name. This thing, when this happens, when two variables occur together and overlap, it's called multicollinearity. It's a great word. It's one of those words that make you sound smart. Just drop that in there. It's up there, I think, with psychoneuroendocrinology. It just makes you sound good. So you're violating an assumption. Always. Almost always you violate an assumption. So what will happen is those b's, sometimes you hear those called beta weights, but the b's, the things, they're coefficients, right? So b sub 1 times x sub 1, b sub 2 times x sub 2. It'll change those. And it'll make them inaccurate, because the math assumes that this doesn't happen. You can probably guess that it's easier to work assuming that it doesn't happen rather than making up a system where it happens this much. You'd have to have different ways of doing it for any kind of amount of overlap. So look at the correlations between x variables. This is actually really easy to detect. So you don't even have to go so far as looking at coefficients of partial determinations or R-squareds. Just do a correlation matrix. So just get a correlation of all your variables, and you'll see that if x variables correlate. Like, it's really not that hard to do. And if they correlate really highly, pick the one you want to use and don't use the other one. Okay. So usually you have to chuck something. You're going to have to get rid of one of your variables if one of them isn't, if you've got a little overlap or something. Okay. Questions on this stuff? Okay, we'll finish this up on Monday, and then we'll talk about some big themes. And of course, if you're watching the YouTube video, that doesn't affect you in the least, because you can just watch the next slide and enjoy that. But at some point, I have to find, oh, there's my mouse pointer, and do. Okay. So last time, or if you're watching the YouTube video moments ago, we were talking about how if you have multicollinearity, if you have many variables that have, this bunch of chairs, I'm going to walk into it. It's got to move. That's out of the way. If you have predictor variables that are correlated, you have a problem. It's called multicollinearity. Okay. So what you've done is you've violated an assumption, and when you violate assumptions, as we all know, it's not good. But the key thing about violating assumptions here is what it does is it makes the test a little more conservative. So the nice thing is you don't make a fool of yourself. You just miss things that were there. So the B's, those are, when you think about how this works with regression, right? So let's look here. You think about how it works with regression. Just break this up here. Just a very quick one. So if we have y hat equals b0 plus b1, x1 plus b2, x2 plus errors. This is a simple multiple regression model. What that's saying is the b's will change. Those b's are constants, right? They're coefficients, right? So if these change, that's going to change how we interpret our results. And it may change, if you violate an assumption, you change things and they're wrong. So what you do really is you just look at a correlation between all your x variables. It's one of your first steps, actually. And then throw something out that isn't correlated. That's all you have to do. All right, so that's where we left off last time. Okay. So there's another assumption you're making, and that's that we have a linear model. We are assuming it's straight lines. And I've told you a number of times that it has to be straight lines, right? But what if it's not linear? Now look at this. Don't worry. Don't get frightened. I know you're frightened already just by looking at that. Don't be afraid. But what this says, this is an exponential function. Remember exponential functions during the lockdown and how the disease was doubling all the time? So that's what we're talking about here. This is a nonlinear, by definition, this is actually an exponential equation, okay? So this is y to the lambda sub 0, so that's like the intercept. So lambda sub 0 to the, so raised to the exponent of lambda sub 1. These are going to become betas. They're going to become b's. To the x times e, that's our left one. That's weird looking. But in fact, when you think about it, okay, all these things here, this is just saying a number times the x number. Oh, okay. So it's just something raised to a power. You look at that and go, oh yeah, but something raised to a power, I can't do multiple linear regression on something raised to a power. You're right, you can't. But the nice thing about this kind of line, and again, if you remember this during the pandemic, you might remember that they would show log functions because functions like this, these kind of exponentials, they go like that, and they go almost straight up eventually, and they become very difficult to read, hard to interpret for a person, because our world, we don't think in logarithms. We just don't. We don't think in exponential functions, we think in linear, because most things around us are linear. So we can turn that into something linear, and all you do is we're going to do the reverse of raising something to a power. So what we're going to do is we're going to take a logarithm. Remember we talked about logarithms, we talked about transformations earlier in the course. So we're just going to take the logarithm of this. And as annoying as that is, if you just take the log of all of this, you end up with this. It becomes linear. It becomes a perfectly beautiful, simple line. That horrible exponential curve now just becomes a nice straight line. We can all deal with nice straight lines. We like straight lines, and also we can do regression on nice straight lines. Once you take the logarithm of everything, one of the things you can do is you can drop these logs. Like they all cancel it. You can get rid of all of them. If you can get rid of all of them, it's equivalent. It's perfectly fine. There's nothing magical or wrong that I did there. Okay. So that's what this in fact has a name. This is called an intrinsically linear regression. So what it's saying is, at its base, if we can play with a little math, we can make it linear. We can make it linear. Just crap everywhere in my way constantly. Okay. So this is called an intrinsically linear regression. It's not linear, but we can make it linear with a very simple mathematical operation, which is just taking the logarithm. Not everything is intrinsically linear. There's a lot of things that are weird curves that you can't make into straight lines. When that happens, you go talk to somebody in the math department. You say, what kind of curve is this? Okay. Or maybe talk to me, or Paul, or Dr. Shant in biology. That's about it. You don't understand it. Like, yeah. But that's why you have other people to talk to for stats. But everything isn't linear. You got to be careful with that. We assume an additive model, right? There's no interactions. We talked about interactions for, 2 months, and now I'm just ignoring them. And think about things like, randomized block can't have interactions. Latin square can't have interactions. And then other things we do because we like them and they're important in psychology, and there is no mention of interactions. So there's no term, again, let's just look at this very basic model that I have up here. Y equals b sub 0 plus b sub 1, x sub 1 plus b sub 2, x sub 2 plus e. There's nothing in there about x1 and x2 together. There's nothing about them occurring together and being more than the sum of their parts. So it's hard to know even what an interaction term would be. We can always, there's nothing stopping us from putting new things in this model. There's nothing stopping us. The numbers don't know where they came from, so that they can't stop us. The problem is that, how do I know what should it be that they get multiplied together, they divide together, maybe it's some kind of weird biphasic function? I just don't know. So you have to do a lot of exploratory data analysis to figure out if you're going to use an equation, an interaction, and it's a non-trivial thing to do. Basically, I'm going to give you the advice of just don't have interactions if you're doing stuff with regression. Okay, and I don't know if any of you guys went to the thesis conference over the week, over on Friday, but there was one person who actually gave a presentation that had a multiple regression, which doesn't happen very often, only once every 3 or 4 years, so I was pretty happy with that. It's like I'm sitting there going, I reached everything, I reached. So how do we select what we're going to use? Because think about, again, the example I've been giving you, I gave you with the 23 variable data set with how many cigarettes you smoke a day, right? So how do we select which of those we use? We're not going to use all 22 to predict the 23rd variable. That's lame. Like, it doesn't help us to predict how many cigarettes people smoke per day if we have to measure 23 other things. That's a waste of our time, right? So how do we know which kind of variables to use? Well, it's very tempting a lot of times to use qualitative variables. There's a problem with qualitative variables. They are numbers. This is all numbers. And qualitative data aren't numbers. Like, if we had hair color, Fine. Let's see. So, let's see. Who's got a pretty, would you say a dark, would you say a black hair or brown hair? Or what?
I think my hair is really, really dark brown.
Okay,
so.
let's go with really, really, really dark brown. And mine isn't. Mine's clear. Is your hair, like if we assigned a number to your hair of 7, just pick the number. It could be 38 if you like, or 2 million, doesn't matter. What does that tell you about Madison's hair and my hair? What are their numbers? Can't tell you anything. That's the problem. It can't, right? So the problem with qualitative variables, and we love qualitative variables, don't we? We like dividing people into groups. Controlled experimental. We love things like that. The problem is we can't always put numbers on them, and this stuff needs numbers, man. So it's okay if it's a binary variable. Okay? So what if we had, I don't know, what's something that's a good, easy binary variable? Oh, yeah. Are people single or not? That's easy, because you get a 0 for single and a 1 for not, or a 1 for single and a 0 for not, no matter what you do. But if you're single and married, or in a relationship or whatever, yeah, I think that works, because if you're single you get a 0, and if you are in a relationship you get a 1. Sure. We couldn't do, are you single, are you married, are you in a, I don't know, polyamorous cube of some sort? I don't know. We couldn't do that. Because there's all kinds of different things that have different qualities. We could conceivably deal with number of partners. It'd probably still be pretty complicated. Let's just even think about hair color, and let's just think about the simplest of all hair colors, like the sort of 4 classics. Brown, black, blonde, and red. And I know there's way more variation than that. We can't code that 1, 2, 3, 4. Because that says then that, I don't know, brown hair is twice the hair red hair is or something. It doesn't make any sense. So there is a way to do this. By the way, if you're going to use a binary variable, it should be 0s and 1s, not 1s and 2s. Because again, nothing and something. Not 1 and 2, because that implies that there's twice as much of something with 2. Let's say we were using, and we just had people, one of my students she asked people's gender identity in her thesis, and she gave people all these options, and all we got were male and female. So, fine, that'd be easy. Male is 1, female is 0. Easy. And we're measuring maleness. What if you're a guy, 0 if you're not? That's easy. Not 1 and 2, that would make no sense. Now there is a way to do this. Also, just as an aside, watch out for Likert scales. They're so tempting. We love them in psychology, don't we? Don't we love the 1 to 7, the 1 to 5, sometimes the 1 to 9. If you're feeling fancy, the 1 to 9. Except, I'm not sure the difference between strongly agree and agree is the same as the difference between agree and neutral. I'm not sure the size of those delineations in a Likert scale are the same. So you got to be careful with those. They're kind of annoying. Also, if you have an experimental variable, different groups, 0 and 1, that's easy, you can do that. 0 for the control group, 1 for the experimental group. So you're not going to have any multicollinearity if you design the experiment. Now, what do you do in a case where you have something like hair color? Well, you do something called dummy coding. Okay? So let's say, we're just going to say there are 4 hair colors. And I know but we're just going to say 4. So, what we do is we do dummy coding. So we're going to say there are 4 hair colors. There's red, there's brown, there's black, and there's blonde. Okay, now, How do we code that? Well, we can't give 1 to red, 2 to brown, 3 to black, whatever. That doesn't make any sense. What we could do is we now have 4 separate variables. We have red hairness, and people with red hair get a 1 there, all the other ones get a 0. We have brown hairedness, 0, 1, 0, 0. We have black hairedness, and then we have blonde, 0, 0, 0, 1. So we now have 4 different variables, but at least we can now do this. So for us in the room right now, we have, I don't see with red hair, but fine, doesn't matter. We have our 4 different colors we could use. And so I would score 1 in the blonde, okay? On all the other ones, I'd get a 0. I don't have brown hair, I don't have black hair, I don't have red hair. Okay, so Jade would be not blonde hair, not red hair, not black hair. Just brown. Make sense? So you can do it, it becomes incredibly tedious, obviously, but it can be done. You're not going to run into this that often. Okay. So what we're doing in the end is we're building a model. This is the sort of simplest kind of model building you can do, is regression modeling. And how do you choose which variables to use? Let's say you have, again, 22, 25, 50 variables, and you want to probably get down to 3 or 4. How do you choose which is which? This is much different from ANOVA, because in ANOVA, what we're doing is we're making a prediction. We're not making a prediction. We're saying this happened. With multiple regression, we're saying this is what would happen. This is how the world works. That's what we're saying here. Okay. I usually start out with a lot of variables. Like I said, the example I've been giving you, my sort of running example with cigarettes per day, that data set has 23 variables. One of them is cigarettes per day and 22 other potential predictors. You don't want to use 22 variables. That's a waste of time. You want to have 3 or 4. It would be great, right? So how did the person who did this work find what the best model was? Because there's, if you've got 22 variables, there are trillions of possible models. So you probably want to get the good one. Well, you could, if there weren't 23, you could do all of them. So if there's only 3 variables, if in your whole data set you have 3 predictors and 1 predicted, so you got y and then x1, x2, x3, there are only 7 possible models. In that case, you probably could look at all of them and compare them on a number of sort of metrics and figure out which one's the best. With 4, there are 15 models. That's not ridiculous. It's not horrible. For 10, there's like, I don't know, I didn't even stop doing the math. There's like a zillion. It's lots. And I'll tell you that the first time I used that data set I was talking about with 23 values in it, I actually used it in a class like this at University of Toronto, and I told the students I wanted them to go get the regression, find the best model. That's all I put. The assignment just said, find the best model to work cigarettes per day. That was it. Here's the day to go. You have 2 weeks, right? So what some of them actually did, and I told them explicitly, please don't do this. Please don't go into the computer and tell it to run all possible regression models, because you will tie up every computer at the University of Toronto, which is literally exactly what my students did. I kept getting phone calls. Are you the guy who's teaching Psychology 305? Yeah, I am. Do you know that you've crashed half the big computers on campus? I'm like, I'm sorry, it wasn't my fault. Kind of my fault, but my students are not paying attention. Because what it would do, the computer would be lost. It's trying to do all these regressions and it can't. And especially 30 years ago, it was even worse. But even today, it would totally tie up your computer. So you don't do all of them and compare them all. So you have to find some way of picking a bunch of variables. So one of the things you can look at are residual plots. And I've talked about this a little bit. There's in fact going to be some residual plot questions on the final. This can be very useful stuff. What this allows you to do is see anomalies, like really weird values. Really weird values. And it can find nonlinear relationships. And I'm going to give you some examples. Oh yeah, I've got some examples coming up. And you can take a look and see a bunch of different residual plots that they're just ones I've hand drawn, and you can see some of the things I'm talking about. So let's look at some residual plots here. Okay, so those are ugly, but I drew them. Let's take a look though. Okay. This one looks fine, the top left here, look, there are just as many above as below. It over-predicts as much as it under-predicts. That's what we want, that's good. This one here seems to under-predict and then over-predict, and it's worse when it's small and then it's, Yeah, that's not good. This one is equally distributed, except as the x value gets bigger, the residual gets bigger. The x value should not have any correlation to the residual, so there's a problem there. And this one, it's obviously a curve. We can't use that variable x4, we can't use variable x3, we probably can't use variable x2 either. We can really only use one of the variables that we've got here, and that's going to be x1. The other ones they're related to it, I have no doubt about that, but we can't use, at least we can't use the techniques I'm telling you about today and I told you about last time. Are there ways? Of course there are ways, but they're much more complicated. And less standard, I guess you'd say. Does everybody understand how these things work? So all these residuals, remember, all residuals are just real value minus the predicted value. So it's the discrepancy between the dot itself and the line if it's just simple regression. Okay.
Real value minus the predicted value?
Yeah, or the other way around doesn't make a difference. It really doesn't matter. It's one or the other. The thing is, we're trying to minimize that, and that's what these are. They're mistakes, they're errors. We just want the errors to have no relationship to the size of the x at all. That's the key thing. So one of the ways we can do this is we can have a computer do it. And you'll think, oh, well, of course, yeah, of course, you have a computer do it. The easiest way to do it, and these are very simple algorithms, these aren't like AI or something. This might actually be a use for AI, literally. That wouldn't be evil. Not a lot of those. Not a lot. Forward selection. What you do with forward selection is, and these are, I'm going to tell you about a bunch of automatic methods for detecting predictors. So what this does is it starts with the x value, the x variable, that has the highest r squared. In other words, the one that overlaps the most with y. Think about those Venn diagrams again. All the x's overlapping with the y. The one that shares the most with y goes in first. And then you add in the next variable that has the next biggest r squared. Of course, that obviously is what you're going to do. Keep going until the jump in r squared is not big enough. Remember, r squared has to go up every time you add a new variable? Well, at some point, it's not going to go up very much, and you go, okay, that's enough, I stop. Now, the question you have to ask yourself is, how much is big enough? Statistical programs, statistical packages are set up with default values. Unless you really know what you're doing, don't touch them. Okay, so when you go to the forward selection algorithm in regression, and it might ask you to adjust, just leave it alone. Okay, what it has is something called, again, you're never going to be asked what this is, but there's this quantity called f star. And what f star is mean squared regression for the variable you're interested in, x1 given x2, divided by mean squared regression for x1, x2. In other words, it's type 2 sums of squares over type 1 sums of squares. And because those are both variance estimates, it's an f. You can't avoid ANOVA, and you can't avoid f-tests. It's just not the way the world works. So you look at this. What this does is it gives you a value, and you say, okay, when this stops being significant, we stop and say, that's it, there's our model. That's all it is. Okay, so all you're doing is every time you do this, when I say you, your computer, whenever it does it, it calculates this, and eventually goes, no, that's not big enough, I quit, there's your model. Okay, that's a thought. you go backwards, which you can probably guess is the opposite. What you do backwards elimination is you start with all the variables in the model, all of them. So let's say with the cigarettes per day thing, you start with that variable, that data set that has 23 variables in it, and you put them all in. And then you start removing ones that contribute the least. So again, what you're doing is you're doing sort of the opposite of what you did before. Which one contributed very little? Like, in other words, looking at that F, has the smallest of those Fs. Let's get rid of that. Then let's do it again. And then let's do it again until it says, oh, you're taking too much out now. Stop. Okay? So it's the smallest F star. And then the next smallest, until eventually you get to F star that's big enough, and you go, no, that's significant, I don't want to stop. I imagine you can guess which is next, which is combining the two of them. This is the one that people tend to use. It's called stepwise regression. In fact, it's so much so that people think that this is another kind of regression. It's not. It's just multiple regression you're selecting the variables using stepwise algorithm. That's all it is. So you're basically combining the two. We start by going forward, using the forward selection model every single time. So you go, okay, what's got the biggest F star? Put it in. And then we check and see, after the first one, is F star still big for all of them? If it's not very big, maybe we'll go through and check all of them again and see if we want to drop one. You can see why you want to do this automatically, because this would be a real pain to do yourself, even with a computer. And basically, you set a criteria for adding and dropping, which again, don't mess with. You have an F star to enter, and you have to make it bigger than the F star to leave. If you don't, what happens is a variable goes in, it gets taken out, it goes in, it gets taken out, it goes in, it gets taken out, and the computer just does that for the rest of your life. So don't do that. I mean, you can obviously stop the process. Unlike, it was more difficult to stop these processes in 1992 when I taught this class. My first class I ever taught was this very course at U of T. And that's when that happened. That whole regression nightmare when I shut down a series of very large, powerful computers at the University of Toronto. Well, I didn't, my damn students did. A couple of which are kind of famous now, and when I see them at conferences, I say, I could still change your mark. If you don't, buy me a beer. It works. Okay, the thing about these procedures is that all they look at is F's. This is where, again, AI could be useful here. This is a case where we could actually have a use for something like, for an AI model. Because we could get an AI model to also look at residual plots. Because these regular algorithms, they're just algorithms. This goes in, this goes in, this goes in, stop, done. They don't care about multicollinearity. They don't care about assumptions being violated. They're just numbers. They don't know where they come from. They don't worry about the fact that maybe it's linear or nonlinear. And again, I think we could probably train an AI to do this. Right? So this is a case, and I don't say these things very often because I think it's quite possibly could lead to the end of our civilization, and I'm actually not kidding. This is one of the places where it could be useful. So let's see, it makes regression models easier, but could destroy the planet. I think we should get rid of it. Anyway, just me, but it would be useful. So what we would want it to do is do all that automatic stuff, but also look for multicollinearity, look at residual plots, look to see if we have non-linear variables. We want it to do that. That'd be great. So this is a case for AI, and I bet there are people working on this. So here's what I've done. I haven't done this very often in my career. I've not played with regression a lot. Like, I've done it like this, but not like in anger, like officially, like on data. When I have, which is only a couple of times, this is how I've done it. I start with a correlation matrix. I just get all the variables and have see they all correlated. It's a very easy thing to do. It's a great place to start. It's basically exploratory data analysis. Now, I immediately pick a subset of variables, so I can throw out variables right away here. I take a look and see is variable x1 correlated with y? Is variable x2 correlated with y? And if it's not correlated enough, and to me, that's below 0.2, I'm not even going to care about the variable. I'm just not even going to use it. I'm just going to throw it away. Okay? Now, if I get a small enough subset of variables, say I got 3 or 4, I'll just look at all the possible variables and I'll go from there. Okay. I'd probably I would try all 3 automatic methods, backward, forward, and stepwise. And I would look for outliers in all the residual plots. And I would look for nonlinear relationships in my residual plots. And then I'd put it away for a week, and I'd come back to it, and I'd do it again. Doing this is interesting. When I've done it, it involves me sitting on the floor surrounded by residual plots. It's not the kind of thing you can do with computer monitors. You need a lot of them. So basically, I've literally sat on my floor in my office with paper all over the place. Oh, this variable's good, that kind of thing. You feel very sciencey. It makes you feel like you're on a TV show or something. It's kind of cool. So then I said, go back and do it again. Okay. So I'm going to give you some conclusions on this, and then we can talk a little bit about how we attack this. We attack these kind of problems. This is an incredibly powerful technique. You're actually building an equation saying we can predict some y from a bunch of x's. That's a pretty powerful thing. One of the key things that people don't care about is multicollinearity, the fact that individual variables correlate with each other. And we don't want that. It violates a big assumption, right? Which we don't want to do. We don't want to violate assumptions. So just because it's an equation, we get this. It's so tempting. You see an equation. You go, oh, that means this causes this. Not necessarily. But it's incredibly tempting because you see an equation. It's like, I told you this equals that. That's causal. When I say something equals something, that I'm making a causal statement. Except that it's not, the model is necessarily causal. That's based on design. That's not based on the technique you used. Okay. So if you're going to pick what the best model is, let me give you an idea here of how we would do this. Let's give you an idea of how we would do this if this was, say, oh, I don't know your final exam. So let's say you had let's say the question said, tell me which is the best model. Because you will have that question. Tell me which is the best model. So we'll use 3 variables. Whoops. x1, x2, x2, x3, x1, x3, x1, x2, x3, and then we have r squared, CP. Okay, r squared, remember what r squared is? It's how much the whole model correlates with y. Okay? Making this on the fly is never easy. 2.5. Okay, so if you take a look at this here, this matrix of values, what we have here is I got 2 columns, well 3, one is the model. And then I have 2 values, one is r squared for each model, and one is something called CP, or C at P. What is C at P? C at P is an attempt to measure bias in a regression model. Okay, it's an attempt to measure bias in a regression model. Okay. So if we took a look at this, and those of you who are watching this on YouTube, well, too bad you can't see this. We have to take a look and see which one has the highest r squared, We want high R-squareds. That's the first thing. And then we also want to make sure it's not biased. What do I mean by that? Does it overpredict more than it underpredicts? We want it to overpredict exactly the same amount as it underpredicts. The expected value of C at P equals P. P is the number of predictors plus 1. Right? Remember that? You have P minus 1 predictors. So, the expected value for P here is 2, 2, 2, 3, 3, 3, 4. It's always one more than the number of predictors. So if you took a look at this, which one of these is the best model? Well, let's start with which ones are the worst. It's too low. 0.1, it's too low. We're not using that one. Well, this, look, so's that. X3 is nice because it's got 0.25 R squared. Of the two variable models, look at X1, X2. It's got a correlation of 0.25, but X1, X2 together should be 0.3. That means X1 and X2 are correlated. We don't want that because that means they overlap. X2, X3 would be 0.3, 0.35. These don't overlap. 2 and 3 don't overlap. This is a really good one. That might be our best one. And 5.2 is kind of high, but it's just one thing, and it shouldn't be your only decision maker, the bias measure. 2 and 3, 0.35, 0.25, 0.35. That's right, we did that. 1 and 3 is 0.4. Oh, no, that one's also got overlap. It's got more R squared, but see, this 0.4 is less than 0.2 plus 0.25, so we're going to get rid of that. This has really nice bias number, the 3 variable one. But again, this isn't that different from this. And remember what I said, that it's nice to have a model where you have 1 or 2 predictor variables, because 1 is a straight line and 2 is a surface, and we can all imagine surfaces and we can all imagine straight lines. The step from 2 to 3 is big. You go to a hyperplane. I would say that's the best model. It has the highest R squared. It has a nice high R squared. The bias isn't horrible, and the predictors don't overlap. Okay. That's the kind of question. That's one of the questions. Basically, it's not the same question, but if you get a question like that in the final exam. All right. And I can give you, don't worry, on the LMS, I'll throw some up there that are practice ones like that you can work on. All that said, any questions on this regression stuff before we can do we have time to do the wrap it up stuff too, so as well, because then we can make Wednesday just Q&A. Right? Good idea? Yeah. All right. So basically the course is done now. So let's turn this YouTube video off, and then we'll record a new one. So.